Oye, Ñolora. So in this video, we're going to take a look at something tangentially related to our ISAT C series. We had a few things that were introduced here that might be useful, although head on over to our regular spreadsheet skills page and look at the basic functions video. The first couple of videos, they might prove useful. You might end up doing a summation in some of this. But one of the things that I really introduced in this series, even though the way that we set up the limitations of the equipment, you probably didn't have to worry about it too much, you will need it as we start to move forward with more advanced scenarios where we start putting in more and more limitations. And I'll also bring up, this is a very important skill that is applied quite a bit in semifinals and nationals if you make it to those competitions. You might apply it in PR3. The thing that I want to bring up is this. So we've got in Fresh Air and in the other C series ones, I introduced the following. Your job is to position the satellite. The satellite is limited to a maximum circular orbit with an altitude of 3,500 kilometers. Further, the satellite cannot drop below an altitude of 400 kilometers. Below this, atmospheric effects can degrade the satellite/the orbit. However, launch notes that the satellite can adjust the apogee higher by 100 kilometers by lowering the perigee by 200 kilometers. Now, this is a common one that I end up using, where it's kind of a trade-off. You can get the satellite to go a bit higher, but you have to balance that by making it go noticeably lower. Now, in actuality, this doesn't necessarily carry over to the spacecraft or the launch vehicle performance to actually make this happen, so this may be a good representation of exactly what happens in real life. But energetically equal would be, in other words, on paper, it should be that if you raise the apogee by 100 kilometers, you would lower the perigee by 100 kilometers and therefore keep the same semi-major axis, at least on an initial glance on that. That being said, we also set it up where it's going to be a little bit more of a challenge for you. Now, many of you have gone through and done a little bit of calculation. You could find out that, okay, well, my limiting factor is going to be how much I can lower my perigee. Well, if I can go down to, say, from 3,500 kilometers, and I could lower my perigee down to 200 kilometers, then that's a difference of 3,300 kilometers. Well, if I divide that by 2, that would be how much I could raise my apogee and I could get more out of it. I'll go ahead and tell you this. In most of these C series, while you're able to actually do that, you probably won't want to do it very much, if at all, because when you're that far out, your sensors won't actually be able to make good contact with the ground. Now, your mileage may vary, so see how you want to apply that and go forward. However, one of the ways that you could approach this is not necessarily by seeing exactly what your hard limits are, but by finding the equivalent circular orbit for whatever orbit you want to have. Because that's a lot of times what you actually do. You go through and you adjust the orbital parameters until you find a really good orbit that you like, and it may not be something that fits perfectly into the raise by 100 and lower by 200. In short, if you raise the apogee by 100 kilometers, you have to lower the perigee by at least 200 kilometers. It doesn't mean you have to lower it exactly 200. You could lower it further down. You could lower it 400 kilometers down. And that's where we want to try and come up with this idea of the equivalent circular orbit. And the other place that this is going to pay off, I'm probably linking this video, and it's very likely you're watching it right now, not for the C series, but in preparation for semifinals or nationals. Because that's a place where you're going to go through and you're going to design an orbit that is very likely going to be elliptical, so you're going to have an apogee and a perigee of some kind. And it won't be just you can't go above 3,500 kilometers, but instead, you're going to see, okay, well, I've got a bunch of rockets, launch vehicles. One of them can get up to 3,500 kilometers. One of them can get up to 3,000 kilometers under these constraints. But that's all listed for a circular orbit. So you need to know, based on your apogee and perigee, your non-circular orbit, what the equivalent circular orbit would be. And I wanted to take this time, since there wasn't as much else to look at in the C series when it comes to the spreadsheet skills, I wanted to take the time, since we're starting to see this a lot more in this series, to go over that. Now, buckle up, because unfortunately, the answer to this is going to be applying math. Now, one of the things that I went ahead and brought up was some samples. So for instance, I could set up a circular orbit that has 2,000 kilometers perigee, or apogee and perigee, and let's say that I'm limited to a maximum orbit, circular orbit, for this scenario that we're going to model of 2,000. So 2,000 is my maximum circular orbit, and I'm maxing that out here as a circular orbit with my first setup. And then I could also, keeping with the same ratio that we had in all of these series, I can raise my apogee 100 kilometers, but I have to lower my perigee by at least 200 kilometers, taking it down to a maximum of 1,800. I could also, if I max this out, let's say that the lowest that I could make in the scenario that we're modeling is 200 kilometers instead, I could then go up to a maximum apogee of 2,900 because I wouldn't be able to safely lower my perigee any more than that. I know in the one that I brought up, Fresh Air, they say that it's 400 kilometers, but I think in Sentinel's Blind, it's actually 200 kilometers. I'll fluctuate in between there, but I've set up some of these where I know that 3,200 is not actually allowed. And let's say that I do a bunch of different things and I find that my absolute best orbit, I just made up some numbers. You're welcome to apply these to something if you'd like. Maybe it is a good solution. I don't know. But let's say that I'm solving, say, a semifinals, and I find that I get a really, really good orbit with an apogee of 2207.15 and a perigee of 326.84. Now, off the top of my head, I'm pretty certain that that's actually allowed because I know that I can go as high as 2,900 on my apogee if I go down real low to 200 kilometers on my perigee. Well, I've only gone slightly above 2,000 kilometers on my apogee, and I've gone way below on my perigee. I've brought it down almost to the bottom, so this is probably going to be an allowed orbit in the simple scenario. But when you get to semifinals, well, maybe one rocket, one launch vehicle, can get up to a circular orbit of 2,000 kilometers with the mass, the weight that you want to load into it. But maybe another one can only get up to, I don't know, maybe 1,800 instead. So here's where the equivalent circular orbit will come in handy. And like I said, buckle up. We have some math to take a look at. All right, I put this presentation together to hopefully kind of do the math in a way that we can follow along. So this is just a brief description on there. I'm not going to read the whole thing to you, but I'm going to pause here. Feel free to pause the video and read some of the notes that I have here on this title page. This is already going to be a decently long and possibly boring video, but trust me, if you don't know how to do this yet, you might want to figure out how to do it. And the last thing that I have listed here, what we're going to be doing is applying the math that many of you would have learned or will learn that's called systems of equations and is usually studied in algebra classes. It's also extremely useful in physics. So for my students that are in physics, this is very much a skill you need to have. Okay, let's jump into it. First off, we're going to look at the example of raising the apogee by 100 kilometers by lowering the perigee by 200 kilometers. This is a pretty common ratio that we've seen in a number of our scenarios, and I have a tendency to default to it. So even if you don't follow along with this perfectly, you'll probably be able to take my general solution from the end and be able to work with it. But the first thing that I've got is here's the systems of equations. I've got two equations. My apogee is going to be whatever the height of my circular orbit is, plus 100 times some number n. So for instance, if my circular orbit started at, say, 2,000 kilometers, and I wanted to raise it by one step, n would be equal to 1, and I would have 2,000 plus 100 is 2,100. Well, that would then be 2,000 minus 200 times 1, and that would be 2,000 minus 200 is 1,800, and that gives me my step. Or I could say instead of taking just one step, I could do two steps with n equals 2. And n doesn't even have to be an integer. I could have n is equal to 0.5. That's half a quote-unquote step. That would mean that I would raise my apogee by 50 kilometers, and I would lower my perigee by 100 kilometers. In this case, by putting in just an n, I'm saying I could take any steps that I want on here and have a general solution. So here's what I'm going to do next. I'm going to go on. I'm going to look at just the equation on the right. My perigee is equal to whatever my equivalent circular orbit altitude is minus 200n. Here's what I'm going to do. I want to solve for n, because n is the thing that I want to get rid of. This is the systems of equations. I've got several unknowns, and I need to get rid of some of them. In this case, we've got a list of all the apogees and perigees for all my different trials. So I want to get rid of n so I can have an equation that is just the altitude, my h circular, my equivalent circular orbit altitude, will be equal to a function of the apogee and perigee, so I can put those in. Okay, my first step is this. It's already shown up here, and some of my mathematical steps I've coded in green. Hopefully you can see a little bit of contrast on that. Maybe I should have done it in blue, but green is kind of my go-to in my class. I'm going to add 200n to both sides so I can get h circular by itself. Ignore the minus peri. That was actually something I was supposed to delete. My next step is, because I want to get n by itself, I've moved it over to the left-hand side of the equation. I'm going to subtract off the perigee value from both sides. Okay, now that I've got that, I want n by itself. It's 200 times n equals those things, so I'm going to divide both sides by 200. We're moving forward, and now I have turned this upper right equation, the one dealing with the perigee, I've moved it around with algebra, and I've turned it into n is equal to the quantity of the altitude of my equivalent circular orbit, the thing that I want, minus my perigee, a value that I have from my trials, divided by 200. Okay, well, if that's what n is equal to, I can then take this mess, as unpleasant as it is, and I can plug it in for n, and n disappears from the equation. I think I also forgot to delete something on this. I apologize. So we've now got, I think this is superfluous. I'm going to get rid of that so that we declutter it. I have taken this, it's equal to n. I've put it into n. Let me go back. So I'm taking this and I'm plugging it in for n. And when I bring that down here, we've got apo equals the height of my equivalent circular orbit plus 100 times n, which is this stuff. Apo equals h plus 100 times, and here is n. H circular minus peri divided by 200. Okay, next step is, I've got a couple steps here. Hopefully I've done this correctly. Apo equals h circ plus, I move the 200 over. I'm still dividing by it either way, so I have 100 divided by 200 times the quantity of h circ minus peri. Now my next step is, I'm going to take 100 divided by 200 is just 1/2, so I'm going to clean that up a little bit. Now I'm going to distribute the 1/2 into the parentheses, and I get this. My apogee will be equal to the altitude of my equivalent circular orbit plus 1/2 the altitude of my equivalent circular orbit minus 1/2 my perigee. Now, if your eyes are beginning to cross because this is a lot of math, first off, if you're one of my physics students, you better be learning how to do this. And even if you're not one of my physics students, this is a good skill to actually have, believe it or not. Wait till we get to the end and see what it will do for us, because this is something that you will, I'm going to say, absolutely need in order to avoid going out of spec in semifinals or nationals. And this is just applying algebra skills. Okay, now what I'm going to do is I'm going to combine the altitude of my equivalent circular orbit. This is 1 plus 1/2, and that gives me 3/2 the altitude of my equivalent circular orbit minus 1/2 whatever my perigee value is. Now I'm going to take that and I'm going to add 1/2 perigee to both sides, and that gets me this. Apo plus 1/2 perigee equals 3/2 altitude of my equivalent circular orbit. We are almost done. Now I'm going to multiply both sides by 2/3 so I can get my equivalent altitude of, or the altitude of my equivalent circular orbit by itself. Finally, we have our answer. The altitude of our equivalent circular orbit will be equal to 2/3 times our apogee value plus 1/3 times our perigee value. So here is our final equation. Now that seems like a lot of work, but again, if you're in my physics classes, this is something that I expect you to be able to do, especially by the end of the year, and the sooner you get used to it, the better. And even if you're not, this is a very useful skill because we're applying algebra in a real-life application. This is the sort of thing that you would need to do to find out if your launch vehicle is capable of getting the satellite up to that circular orbit, because our performance tables for our launch vehicles are almost always designed around circular orbits for the rockets. But you may not necessarily want a circular orbit for your solution, so you need to be able to turn your elliptical solution into an equivalent circular altitude. Now, this analysis can be repeated with any trade-off that you have. So for instance, if you can raise the apogee by 100 kilometers by lowering the perigee by 150 kilometers instead, then go back through this analysis. I know you're not stoked about that, but it could be the difference between getting a good score and getting a 0. Just go through this analysis again and replace the 200 with a 150 and repeat the analysis. Or replace the 100 with whatever you're given for raising the apogee. Okay, now that we've got that, we know that our equivalent circular orbit should be equal to 2/3 times our apogee value plus 1/3 times our perigee value. Now that I've done that work, I can come in and do the following. I'm going to call this equivalent, circ. This is the altitude of our equivalent circular orbit. I'm going to teach my spreadsheet the equation we just derived. We said that it was equal to, the apogee times 2 divided by 3, 2/3, and then we're going to add that to, I believe, I will double check, the perigee times 1 divided by 3. Yeah, added together. And here we go. We've got 2,000 is our equivalent circular orbit. Now, in the first one, that's kind of obvious because it's a circular orbit of an altitude of 2,000. In the second one, we know based off the trade-off that I raised my apogee by 100 kilometers and I lowered my perigee by 200 kilometers. So we know this should have an equivalent circular orbit of, and look at that, 2,000 kilometers. The next one, I drag it down, and here was our absolute limit. We're going down as low as the perigee would allow, but we still have a 2,000 equivalent circular orbit. Now here's where it starts to pay off. Let's say I'm not paying close attention or I did my numbers wrong, and I think I can go up to 3,000 kilometers for my apogee and my perigee at 200. Well, for this, when I drag it down, we see that I'm now greater than a 2,000 equivalent circular orbit. So I could put in an if conditional statement that basically says, hey, throw an error at me now that you're calculating this that says your equivalent circular orbit is too high, you are out of spec. You will not get the points that you think you will. Or, in semifinals, you have to find yourself a launch vehicle that can get up to this circular orbit. Which brings me to the last one that I had. Now this one we said should be allowed, but if this were semifinals or nationals, I don't necessarily know which rockets can and cannot do this. So I drag this down, and we find a very important number. For this very strange orbit that we've got that may be doing wonders in solving your scenario, we now know that it has an equivalent circular orbit of 1,580 kilometers. So, instead of having to go with an expensive, big, heavy rocket that could get up to 2,000 kilometers, maybe we can go with the cheaper one and get a better score as a result, because all we need it to do is get our satellite up to an equivalent orbit of 1,580 and some change. You might shoot for maybe a 1,600 just to be on the safe side. But here's how you can get this number. And one, check that you're actually still within specifications, the requirements for the ISAT C series, and get a head start on some skills that will hopefully pay off when you get to the highest levels of competition. Alright, that's the main thing that we had for you in this video. While it isn't exactly tied to the C series as part of key things that you would need, it's a good thing for us to look at because the C series does introduce a lot of this, and it's good to get used to this now. You may be applying this in later series, but we may also have additional videos that we want to show for STK functions in there. Alright, hopefully this was useful for you. Until next time.